Welcome back, everyone. Today in Abstract Algebra, we're going to talk about cyclic groups. Cyclic groups are one of the simplest types of groups we can find, and some of the simplest groups to work with, but they're also very useful. So let's start by setting up some notation. So definition, let G star be a group. Let G be an element of the group. Then what I want to set up is notation. What does it mean? What does G to the n mean in my groups? So first, it's just E if n is 0. If n is a positive integer, it's just going to mean G star G star G star G, where this is G n times. And notice that it doesn't matter. In principle, I should have a bunch of parentheses here for the associativity. Because of the associativity property, which G satisfies because G is a group, it doesn't matter how I put parentheses. So this has a well-defined meaning. So this is if n is bigger or equal to 1. And if n is negative, what it means is that, we're going to do this is equal to G minus 1 to the absolute value of n, and now absolute value of n would be positive. So it is G to the minus 1 star G to the minus 1 star G to the minus 1, and this whole thing is done absolute value of n times. And this is what it means if n is less or equal to minus 1. So this is what we mean by power. And by the way, note that if the notation is additive, so if we are talking about a group and the notation is really an additive, what we call an additive group, then G to the n is really G. And now with the operation, which is addition in this time is just addition, and this is supposed to be n times. So it is really n times G. So it depends then what the operation is, what this means, but it's just G to the n. It will denote when we operate n times. Okay, so now we are going to continue with that definition, and then we say that then G, or the set generated by G, is going to be, well, the set of all powers of G as n runs over all the integers. So it is G to the minus 3, G to the minus 2, G to the minus 1, 0, which is E, and G2, and etc. Okay, so it's that whole set. And our very first task is going to prove that this is a subgroup of G. But let me show you that, well, sometimes this looks like an infinite set, but many times this is just a very finite set. So if we have Z modulo 4 Z under addition, then what is the subgroup generated by 1 mod 4? Well, it will be the powers of 1, which is in this case 1, and then 1 plus 1, which is 2, and 1 plus 1 plus 1, which is 3, and 1 plus 1 plus 1, which is 0, and then plus 1 would be 1 again. Oops. Oh, what just happened? Okay. All right. So this is the entire Z modulo 4. And if I do what is the subset generated by 2, it would be the multiples of 2. So start with 0, and then 2, and then 2 plus 2 is 4, which is 0. So that's it. It's just 0 and 2 as considered as classes modulo 4, just like as these were considered as classes modulo 4. So the set generated by G is not always infinite, as in many cases it's just a finite set. All right, so what I want to prove is, in fact, the following proposition: let G star be a group, and let G be an element of G. Then this subset generated by G, again, powers of G as n runs through the integers, is a subgroup of G, meaning that these one with the same binary operation is a subgroup of G star, right? That's what we mean. So how are we going to prove this? Recall that we had a theorem or a corollary that says let G be a group and H contained in G, then H with a star is a subgroup if part A, H is non-empty, and part B, if G and H are in H, then G star H inverse is in H. So we are going to use this to prove that the set generated by G is actually a subgroup of G. So let's do that. Here is the proof. First of all, G, first note that G is in the subset generated by G. So this is not empty, and that proves part A of our theorem that identifies subgroups. When for part B, let A and B be elements of the subset generated by G, then, well, they are generated by G, so they have to be powers of G. So G, A is G to the N, and B is G to the M for some N and M integers. And therefore, how much is A star B inverse? That will be G to the N star G to the M inverse. And that is G to the N star G to the minus M. And by the way the powers were defined, this is G to the N minus M. And this N minus M is another integer, and therefore it belongs to the subset generated by G, and thus, by the theorem, this is a subgroup. So that is the end of this proof. Great. So we have that this is a subgroup, and then we can actually now define finally what it means for a group to be cyclic. Let G be a group. Then we say that G is cyclic if there is some element in G such that G star is actually the group generated by G under star, i.e., G as a set is the same as the subset generated by G, i.e., for every H in G, there is some integer such that H is actually a power of G. So that means that G is cyclic. Let me show you some examples. So for example, our beloved, the integers is cyclic because, why? Well, they are generated by 1. And that is easy to see because if I have any integer n is 1 plus 1 plus 1 n times. If n is positive, so and this is what we would say n times 1, or in the group theory notation, that is what is 1 to the n, as we've defined before. So this we get any integer n from 1, and if n is negative, then it will be minus 1 plus minus 1 plus minus 1, absolute value of n times, if n is negative. If n is 0, then we get 0 times 1. So it's cyclic. By the way, notice that z is also generated by minus 1. So when I said that a group is cyclic, if there is some g such that this happens, that g may not be unique. And in fact, you can see that z is generated by 1, but it's also generated by minus 1. In general, if a group is generated by g, it is also generated by g inverse. Okay, here's another example. So is z modulo 4 z under addition cyclic? Yes, we've just seen that if I look at the subgroup generated by 1 modulo 4, I do get 0 and 1 and 2 and 3 mod 4, which is all of it. So yes, it is cyclic. How about, we've talked about this before, about this other example of a group with 4 elements. How about this group? Is this group cyclic? This one is not cyclic. And to prove that it's not cyclic, now what I have to do is actually try to generate it. So I have to look at all the subgroups generated by one element and see if any one is the entire set. So what happens if I generate with the identity? I just get this subgroup that is not the entire thing. What is the subgroup generated by this element? Well, I get the identity and also itself. And then when I add it to itself, twice this element is 2, 0, which is 0, 0. So that's all I get. If I do the same with 0, 1, I get this subgroup. And if I do the same with this other element, I get also another subgroup, which has order 2. So they are all included, but none are the total. So it cannot be cyclic. There is no generator for this group. So it is not cyclic. So once again, you see that this one is cyclic, this one is not cyclic. And that's another way to distinguish groups. Once we get into the business of classifying groups, this is another way we can say, no, these two groups are not the same group. They are not isomorphic because this one is not cyclic while this one is cyclic. Let me give you another example. How about the real numbers under addition? Are they cyclic or are they not cyclic? And it turns out this is not cyclic. There are many reasons. One reason you can check is that, well, R is uncountable, but the integers are countable. So for a contradiction, suppose it was cyclic, then there would be some real number such that the subgroup generated by G is all of the real numbers. Okay, so these are all the multiples of g. This is under addition, so they are just multiples of this one real number. And this would give me a map from the integers to the real numbers that is surjective, that for every n, I get n times g, and I get all the real numbers. This is surjective, but this is impossible. This is impossible because this would give me a surjective map from something that is countable to something that is uncountable. And that is an impossibility. We cannot have such a map if you've seen enough set theory about this. But let me actually show you in another way that this cannot be the case. And in fact, what I'm going to show you is that even the rational numbers are not cyclic. So let's show that the rational numbers are not cyclic. Is not cyclic. So how could the real numbers be cyclic when the rationals are not cyclic already? So again, suppose that that we have some number, some rational number, such that the subgroup generated by G, so the multiples of G, are actually all the rational numbers. Okay, then, for example, the number 1 is in here. So there is some n1, an integer, by the way, such that n1 times g is 1. And that would tell me that actually g is 1 over n1. Okay. But then how can that possibly be? But you see now what would be g? G would be all the multiples of these fixed rational number 1 over n1, which is, well, n over n1 as n runs over the integers. But these are rational numbers such that the denominator divides n1. I do have 1. I have all the integers, and I have denominators with n1, but I don't have, for example, 1 over 2n1, for instance. So, for example, 1 over 2n1 would be something like g divided by 2, and this is not some multiple of g with n an integer, because that would tell me that the integer that I need is a half, which is not an integer. So that is the contradiction that I was looking for. So it is impossible. I cannot have one generator of the rationals, so the rationals are not cyclic. Okay. Let me give you another example of a cyclic group inside the rationals this time. So I'm going to consider now the rationals under multiplication, and which is actually a subgroup of the real numbers under multiplication. So if you want, you can consider what I'm going to do as a subgroup of either one. But we can take, for example, as a subgroup that is cyclic, the powers of a given number. So for example, I'm going to take the subgroup generated by 2 under multiplication. So the subgroup is the powers of 2. So there is 1 and 2 and 4 and 8, etc. and also a half and a fourth, etc. This is a subgroup under multiplication. If I do the subgroup generated by -2 instead under multiplication, that one is different. -2 here, the powers of -2 are going to be 1 and -2, and the square is going to be positive, and the cube is going to be negative, etc. And then I'm going to have 1 over -2, and 1 over 4, and 1 over -8, etc. So those are going to be two different subgroups of the rationals under multiplication that are cyclic. Similarly, we just proved that the rationals under addition are not cyclic, but of course they do have subgroups that are cyclic. For example, the integers under addition are cyclic. Or for example, I can generate with a half a cyclic group, and the cyclic group generated by a half will be all the multiples of a half. So I have 0 and a half and 1 and 3 halves and etc. So what I get is and -1, etc. So that what I get all the rational numbers that have denominator 1 or 2. Okay. Let me give you now some subgroups in modular arithmetic, some cyclic groups in modular arithmetic. Let's consider z modulo 9, but I'm going to consider multiplicatively. So to consider multiplicatively, what I'm going to do is consider the things that are invertible in z modulo 9. So I'm going to consider that multiplicatively. So these is classes modulo 9 that have a multiplicative inverse. Whoops. That have a multiplicative inverse. So what are those? It turns out that those are, in general, if you have in z modulo and z, those that have multiplicative inverses turn out to be those classes between 1 and n such that the GCD of a and n is 1. So in this case, there are the numbers from 1 up to 9, relatively prime to 9. So that will be 1 and 2 and 4 and 5 and 7 and 8 modulo 9. Okay. And you can see that these are actually, they form a group under multiplication. So for example, 2 times 4 is 8, which is another one of these units, modulo 9. That's what these are called also. These are the units, modulo 9. And in some books, I think in Judson, this is called U9, the units modulo 9 under multiplication. So for example, 2 times 4 is 8, 4 times 5 is 20, but 20 is congruent to 2, is 20 is 18 plus 2. How about 4 times 7? That is 28. 28 is 27 plus 1. So this is 1 modulo 9. And what that means, why are you doing this? Oh, okay. My goodness. Modulo 9, what that means is that 7 is the multiplicative inverse of 4 modulo 9, because it's the number that when I multiply by 4, I get 1. Okay, so what I want to actually show is that U9, the units modulo 9, is a cyclic group. So let's see why. So U9 is cyclic. And as I said, U9 is 1, 2, 4, 5, 7, 8, mod 9 under multiplication. And I claim that actually it is generated by 2. So let's see what are the powers of 2. So I have 2, then 2 squared is congruent to 4, 2 to the cube is congruent to 8, and then 2 to the 4, well, 2 to the 4 will be 2 times 8, so it's 16, and 16 is 7. 2 to the 5 will be, I don't need to keep using the big numbers. I can say 2 to the 4 times 2. I know that 2 to the 4 is 7. So this is 7 times 2, and 7 times 2 is 14, which is 5. 2 to the 6 is going to be 2 to the 5 times 2, which is 5 times 2, which is 10, which is 1. So now I see that I have 1 and 2 and 4 and 5 and 7 and 8. So actually, all the powers of 2 up here go through every single element of U9. So in the order that they appear is 2, 4, 8, 7, 5, 1, which is equal to U9. So that means that because this is true, it means that U9 is cyclic and generated by 2. There are other generators, but 2 is one of them. Let's see if U8 is cyclic. U8 would be the numbers from 1 up to 8 that are relatively prime to 8. So it's actually just 1 and 3 and 5 and 7 mod 8. So there are 4 elements. And let's see what happens. Let's see what are the powers of 3. Is it the powers of 3 would have 1 and then 3. 3 squared is 9, but 9 is already 1 mod 8. So actually, this set is just 1 and 3. So that doesn't give me all of U8. So this is not a generator. What about, let's try with 5. I have 1, I have 5. 5 times 5 is 25, and 25 is 24 plus 1 is 1. So that's as much as I get. And 7, 7 times 7 is 49, or rather, 7 is minus 1 modulo 8. So minus 1 times minus 1 is 1. So actually, I just get 7 and nothing else. So none of these is equal to U8, and therefore U8 is not cyclic. So some of these unit groups modulo n are cyclic, and some of them are non-cyclic. Okay, so I'm going to stop here, and next time we're going to prove some theorems about cyclic groups.